What's going on, my friends? Welcome back. So today we're going to watch another Physicist video. Before we get into it, two things. One, the alpha for KelVPN, my quantum-proof VPN, is essentially ready. We're just trying to implement a way for you guys to be able to log in when you download it. So everything works. We're doing this so we can test, all of the stuff on our side, and so it'll be free. So that's exciting. So next week is what we're aiming for. And then the second thing, I can finally tell you guys what I'm planning for this second venture I've mentioned before. So if you guys have ever read Morning Brew, you'd get a pretty good idea of what we're going to try and do. So it's completely free. This will all be completely free. You just sign up with your email, and we'll send you an email every single day with our newsletter, the Daily Dance. And it will be like bullet points, there'll be some memes, quotes, and it's going to break down the newest science with links, maybe in bullet form, and the latest on business, geopolitics, world business, as well as new tech that's emerging. I think this could be really useful for people in business, for people who are just passionate about keeping up with science, because it's not done well anywhere, really. So I'm super excited about this. It's going to be completely free to you guys. Kind of already do it in my head every day. I'm passionate about keeping up with what's going on in science, whether it's space, physics, everything. I love it. And then combined with that, what I'm going to do is then live stream on Twitch me reading our daily newsletter every single day. And then with that stream, I can, chat with you guys and watch YouTube videos, do whatever, right? And then I'll upload them to YouTube as well. So I think that'll be a fun little system. Apparently it's National Girlfriend Day, so I just want to say a big hello to all my girlfriends out there. That's a joke.
Black holes are the most powerful things in the universe, strong enough to rip whole stars into atom-sized pieces. While this is scary enough, they have an even more powerful and dark property: they might delete the universe itself. Black holes in a nutshell. A black hole appears when an extraordinary amount of matter is concentrated in a tiny space. At their center, gravity is almost infinitely strong, and whatever gets too close is ripped into its elementary particles.
You know how I do it. I just like to nitpick everything. It is infinitely strong, at least according to the equations of general relativity.
Not even light can escape black holes, and so we perceive them as spheres of blackness. If you were to fall into a black hole, nothing bad would happen until well after you crossed its outer border, the event horizon.
That's also not true. You can actually get crushed. There's all sorts of things that can happen to you before you cross the event horizon.
Imagine this as swimming in a river that ends in an enormous waterfall. As you float along, imperceptibly, the stream gets faster and faster, even if you can't see the waterfall yet. You could swim to safety until, without even noticing it, you cross the point of no return. No matter how fast you try to swim now, the stream will pull you towards certain death. Nothing can escape a black hole waterfall once it gets too close.
Here's something you might not know. Dark energy can actually escape a black hole, no matter what size the black hole is, and no matter how close the dark energy is to even the center of the black hole. This is because dark energy isn't affected by gravity at all. Dark energy is what causes the universe to expand faster and faster, we think. So this means it actually has an effect opposite of gravity, since gravity pulls things together, right? The only thing in the universe, as far as we know, that is not affected by supermassive black holes. Have you ever wondered if black holes eat dark matter? Well, if you do the math, you'll actually find that black holes will use both normal matter and dark matter as like a food source. But the normal matter will dominate the growth of the black hole, even over like enormous cosmological timescales. Even when the universe is like 1 billion times older than it is right now, black holes will still be like 99% normal matter and less than 1% dark matter. So dark matter is not really a good food source for black holes, nor is it, like, information-wise, an interesting one. So what it gains from eating dark matter is not really any different from like shining a flashlight into it.
This border completely separates black holes from the rest of the universe.
So if you want to know what happens to someone who falls into a black hole, you should go check out the other video that we reacted to of Physicist. I'll put a card up on the screen if you want to watch.
Can't access them unless we're willing to never return. So there's no way of telling what's really going on inside black holes, but we have a few ideas about what's going on right at their very edges. Black holes radiate their mass away, like a hot pot on a stove losing its water as steam. This is called Hawking radiation. Black holes constantly lose an extremely tiny amount of their mass.
Okay, I think we're going to have to talk about Hawking radiation a bit in this video, so we'll get there, but let's do some more watching. And yeah, maybe I can actually give you guys a bit more information as to what's really going on. Because if you watch the other ones, I've told you the common explanation that people like to give, even including Hawking himself, is a kind of a lie. It's like a simplification. But anyway, let's keep watching for now.
A process that's unbelievably slow. It will take.
He's just visualizing just then. Like that's not what's really happening.
Take a black hole with the mass of our sun 10,000 billion years to lose 0.0000001% of its mass. This is happening constantly and unstoppably, and as it goes on, it speeds up more and more. In the far, far future, when the last star...
What he's showing is not actually what's happening. So in 1974, when he famously derived Hawking radiation for the first time ever, this was the calculation that he made. He calculated the difference in the 0-point energy in quantum fields from curved space around the black holes to flat space infinitely far away. So the result of this was what determined the properties of the radiation that come from black holes, not from the event horizon exclusively, but from the entirety of the curved space around it. So the major problem with the explanation that he gave of his own theory is that he takes a calculational tool, the idea of these virtual particles, and treats them as though they're equivalent to physical reality. In reality, what's actually happening is that the curved space around the black hole is constantly emitting radiation due to the curvature gradient around it, and that the energy is coming from the black hole itself, causing its event horizon to slowly shrink over time, right? So black holes are not decaying because there's an infalling virtual particle carrying negative energy. That's another fantasy that he explained. Instead, black holes are decaying and losing mass over time because the energy emitted by this Hawking radiation is slowly reducing the curvature of space in that region. Once enough time passes, and that duration is enormous for realistic black holes, they would have evaporated entirely, right? So this Hawking radiation is not the emission of particles and antiparticles from the event horizon. It does not involve an inwards falling pair member carrying negative energy, and it shouldn't even be exclusive to black holes.
And for trillions of years, black holes will become tinier and tinier until they evaporate and disappear, leaving behind just a bit of radiation. But this is a problem, because in the process of disappearing, black holes might delete something fundamental: information. 2. What is information? Information is nothing tangible. It's typically understood as a property of the arrangement of particles. What does this mean? Imagine a bunch of carbon atoms. Arrange them in a certain way and you get coal. Arrange them in a different way and you get a diamond. The atoms are the same. What changes is the information. If we make this more complex and add in a few more atoms, we get a banana. Change the arrangement of the atoms and we get a squirrel. The basic building blocks of everything in the universe are the same and part of a bird or a rock or a cup of coffee. Without information, everything in the universe would be the same. According to the theory of quantum mechanics, information is indestructible. It might change shape, but it can never be lost. For example, if you burn a piece of paper, you get ash. That ash will never become paper again. But if you were able to carefully collect every single carbon atom in the ash and measured the exact properties of the smoke and heat radiating from the fire, you could, in theory, reconstruct the paper. The information of the paper is still in the universe. It's not lost, it's just hard to read. If you could somehow measure every single atom and particle and wave of radiation in the universe, you could see and track every bit of information there is. Hypothetically, you could see the entire history of the universe right back to the Big Bang. And here, black holes trip us up. Information tells us how things are different from each other and what used to be what. Black holes do the opposite. They take different things and make them the same. They destroy information. This creates the information paradox, and this is a serious problem. The information paradox.
There's been a bunch of proposed solutions to this information paradox, and we'll talk about a few spaced out over in this video. including the firewall paradox, where information is assumed to burn up before it enters the black hole, the string theory's fuzzball solution, where black holes are thought to have like indistinct boundaries, and 2 others, Planck stars, and first we'll talk about right now. So a lot of those solutions require rewriting the laws of quantum mechanics or Einstein's theory of gravity, the 2 pillars of modern physics, right? Whereas this quantum Hare theorem might be able to do it by bridging the gap between general relativity and quantum mechanics using like a new mathematical formulation, right? So black holes might just be more complex than we thought, or hairy. So as matter goes into it, falls into it, it leaves like this faint imprint in the gravitational field. This imprint is referred to as quantum Hare, and will provide like the mechanism by which information is preserved during the collapse of a black hole. But unfortunately, there's no obvious way to test this theory, like with astronomical observations. The gravitational little fluctuations would be way too small to measure. There'll be a lot of scrutiny, though, in the theoretical community with this, so I guess this is fairly new, so we'll see what happens.
It's fundamental for all our laws of physics that information can never be lost. Existing, not existing, without information, everything is relative. When it comes to our understanding of reality, we need absolutes. How could we solve this paradox? There are a few possibilities. 1. Information is lost, irretrievably and forever. This means we have to nix all our laws of physics, throwing out a lot of stuff that's worked very well so far and start from scratch. What those new laws of physics would look like, or what that means for us, nobody knows. This is a little frightening, but also kind of exciting. 2. Information is hidden. Maybe a little part of the black hole splits off and forms a baby universe. The information would be transferred into this new, weird place where we could never observe or interact with it, but technically it would not be lost. It's like having a broken hard drive with all your family photos that you could never access. Sure, it's nice that they've not been deleted, but also not very helpful. Or maybe black holes don't disappear completely after the end of their life cycles, but a little piece is left, an information diamond.
So what about if black holes are fuzzballs? This would also resolve the information paradox, because in string theory, we found that all the mass of black hole is not getting sucked into the center. The black hole tries to like squeeze things to a point, but then the particles get stretched into these strings, and these strings start to stretch and expand, and it becomes this fuzzball that expands to fill up the entirety of the black hole. Alright, that's enough of the fuzzball stuff, because there's still absolutely no evidence for string theory.
If everything that falls into the black hole is stored on its event horizon, like a clown car filled with an infinite amount of information clowns. But there's a third option: information is safe after all, not lost or hidden. Perhaps we've just been looking at this whole thing the wrong way. We know that black holes trap information and might delete it later, but we never thought about what they do with it in the meantime. Where do black holes store their information?
Planck stars. So they're these theoretical objects in which a massive star breaks down, and what would typically become a singularity, where the density of spacetime is infinite, meaning nothing can escape, instead becomes this Planck star, where the collapse is basically stopped by a form of repulsion that's created by energy density coming from the Heisenberg's uncertainty principle before the object reaches an infinitely dense point. This basically results in an object that's not much bigger than the Planck length, which happens to be the smallest possible measurement. So because this replaces an inescapable singularity with something just really small, but not infinitely dense, just bigger than the Planck scale, but not by many magnitudes, it would resolve a lot of paradoxes surrounding how matter and energy work around black holes, but not without creating some new questions, obviously, along the way. So it does away with the information paradox, because there's enough volume and density in a Planck star to basically make sure that information about matter and the quantum states about matter that get swallowed by a black hole don't get destroyed. Weirdly, though, believe that these Planck stars in the middle of a black hole would continue to grow if matter kept falling in. So basically, the Planck star would consume so much that it would intersect with the event horizon, causing all of this information to be expelled in a flash. And finally, the Planck star would also do away with the firewall paradox, because there's a bunch of interesting implications for how the universe might bounce and crunch.
Cosmic housekeeping. Let's create a black hole with dirty laundry. First, we fill up a room with laundry baskets. The more laundry you want to store, the more baskets you put in the room. But at some point, every single basket is full and the room is completely stacked. Not a single extra sock fits in. The room is at maximum capacity. But if we still squeeze the sock in with a lot of energy and violence, the room collapses in on itself and forms a black hole. But the capacity of the room itself has not changed. Fitting in more stuff or information is still impossible. So what happens if we throw more laundry into it? The room itself gets a little bit bigger to make space for the new information. It turns out a black hole grows its surface by a tiny pixel for each bit of information we throw into it. In a nutshell, more information means more surface area. The information gets painted on the surface, similar to what happens when we throw a stone into a pond. After the stone sinks to the bottom, we can't see it anymore, but we can tell that something went in from the ripples on the surface of the pond. Even the smallest black hole can store more information on its surface than all the data ever produced in human history. They do this by storing information in a type of pixel that is unbelievably tiny. Black holes are the ultimate hard drive. This is a bit like taking a paperback and turning it into an ebook. Two things that look completely different, but their content is the same. It's just encoded and memorized in another way. Black holes swallowing stars and planets is a bit like transferring a whole library onto an e-reader. This solution is called the holographic principle. But if it's correct, then everything we thought we knew about the universe is wrong. The universe is a hologram. If information is actually stored on the boundary of a black hole, the Hawking radiation has a chance of learning about the information encoded there and can carry it away.
It's one thing to ask how can you decode the Hawking radiation, but you also might ask how complex is that task to do that? Well, it turns out it's extremely complex. There's some fun proposals called the Python's lunch that explains how you might actually be able to do it.
So, information is not lost when black holes fade away, and we do not need to redo physics. The information paradox is resolved. But we still have to change our understanding of reality in a fundamental way.
Alright, let's talk about this firewall paradox. So, like in 2012, the firewall paradox kind of got like this reimagining. The firewall is like this hypothetical phenomenon where someone falling in would encounter like a high energy quanta essentially at the event horizon. Conventionally, we've pretty much assumed that if a black hole was large enough, someone falling in wouldn't notice anything unusual as they fall in. But in this scenario, which we call the no drama, the gravitational forces wouldn't be extreme enough until you get to the point inside the black hole called the singularity, right? But if that's correct, as someone crosses the event horizon, so if this firewall paradox is correct, as someone crosses the event horizon, they'll pretty much encounter like a massive wall of fire that will incinerate them on the spot, right? No one's been able to explain, though, exactly what happens when a black hole consumes particles, or how information might leak out of a black hole in the form of like quanta, right? The traditional understanding has always said that all matter consumed by a black hole would immediately be lost to outside observers once it's sucked into the event horizon. An astronomer basically figured out that if entanglement between an infalling particle and the outgoing particle was like broken, then a bunch of energy would be released, creating this black hole firewall at the event horizon. And that would prevent us from observing the information. Other physicists have even proposed that the outgoing and infalling particles are somehow connected by like wormholes.
That basically means that three-dimensional stuff is encoded on a flat surface. We have a name for this, a hologram. A hologram is like a 3D photo, a flat piece of plastic that encodes a three-dimensional image. A black hole is like a hologram because everything inside it is encoded on its event horizon. A person inside a black hole would experience their usual three-dimensional life. But for us on the outside, they are flattened images on the surface of the black hole. The consequence of this is counterintuitive, but stay with us for a moment. Black holes are very extreme objects, but they're still bound to the same rules as everything else. So if this crazy duality between 2D and 3D works for black holes, then it might work for the whole universe and you in it. Since a person inside a black hole would not realize that they're encoded on a flat surface, we might share the same fate. You really might be stretched over a flat screen at the end of the universe. The science behind this is complicated and really weird, with toy universes to play with, string theory, and a lot of maths. We'll talk about this more in another video. Regardless of what the true nature of the universe really is, we just know that it's strange and complicated, and we have to do a lot more physics to understand it. But black holes might be key to understanding the nature of reality itself. This video was supported.
Another great video by Physicist. I enjoyed that. Hope you guys enjoyed. I'll catch you next time.